Hello, my name is Brian Manning, and this is the energy absorption tile final presentation. The key question we are trying to resolve with this project is, can kinetic energy from footsteps be efficiently sourced and stored as a viable renewable energy source? In a world where everyone is trying to come up with new ways to save energy and be resourceful, why not figure out a way to convert something as simple as a footstep into energy? There is already some work being done in this area, but it is a broad and upcoming technology, which so far takes two approaches. One being the application of tiles with small electric motors attached to them. When people step on these, the displacement turns a rotor, which then creates electricity. Another solution to this problem is through the use of piezoelectric materials, which is the method being studied in this report. Based on the question on the project, this would heavily fall under the green category, while also being somewhat in the gold category, since the users of this project would be saving money in the long run. So the objective of this test is to study the relationship between mechanical and electrical energy through the use of piezoelectric materials subject to different loading cases. Since piezoelectric materials are quite expensive, small 41mm discs were chosen for our testing. Due to their size and build quality, almost all of the connections had to be resoldered, even before we tested them in different configurations. These specific discs are made out of lead zirconate, titanate, and are commonly used in pressure sensors, audio equipment, and even ultrasounds. For this test, for the method of collecting data for this test, our first idea was to design a drop test device and drop various weights from this fixed certain height. After receiving the discs in person and then also talking to Professor Hoover, we decided using the load frame with a cyclical load would give us far more accurate and repeatable data, not to mention all the time savings that would come with the use of this. Dropping weight over and over again would just be too tedious and very boring, and the load frame can do easily 100 cycles in a minute. We completed 2 rounds of testing, the first one being more focused on learning what kind of waveform we wanted while also perfecting the circuit and measuring devices. In that first round, we were mostly using the oscilloscope, but in later testing, it was kind of backfeeding the circuit and running some of the results, so we had to switch it out for just a voltmeter, or a multimeter and a camera. So yeah, the second round of testing included all the data collection, which included the single transducer at 4 different loads, as well as the series and parallel configuration, both at the same load. Each case was run twice to study the repeatability and possible error, which will be discussed later. For any experiment, it's very important to identify all the variables and parameters. Variables for this test are the voltage measured in volts and the time measured in seconds. Both of these would be recorded off of the multimeter and camera. And then most of the parameters for this test came from the load frame, which include the max load, speed, speed at which the load was applied, capacitance, which was 47 microfarads, and then number of cycles was also recorded for each test.
The equipment used in this lab are commonly found components in mechanical engineering labs, with the exception of the 41mm piezoelectric tiles. Some examples of components we used were a 47 millifarad capacitor, 4 rectifier diodes, a light, breadboard, wire, switch, a multimeter, and a 1K stack 16 load frame. We kept costs to a minimum by using components already used before in Clarkson's MAE lab. The only thing we had to purchase were the piezoelectric tiles, or also known as transducers, at around $10 for a pack of 10. Our test plan includes gathering materials, designing the circuit, which is shown below, and connecting the rectifier diodes in order to convert AC voltage from the transducers to DC voltage to charge the capacitor we are using to discharge on the light. We had to incorporate the load frame to keep testing parameters consistent. That way this test can be repeatable. Our goal was to run multiple tests for each parameter. On the right is the Gantt chart. This was made earlier in the semester. We divided it into 5 3-week periods which shown on the Gantt chart, we fell behind a little bit in periods 2 and 3, got back up to speed, and then also fell back again a little bit until we completed the whole lab within the last 2 weeks. Here is our procedure of the actual data collection part of the lab. It consists of connecting the circuit, putting the transducer into the load frame, then controlling the parameters with the load frame so that we can see the change in results from altering only one variable at a time and controlling the others to be able to be consistent. The main test variable that we changed was the comparison of different cyclic loads, for example, 5 pounds, 10 pounds, alternating, as well as the parallel and series of 2 transducers. Here are some testing pictures we ran for each test parameter. On the left, it shows the light going off from one of our videos where we discharged the capacitor in the circuit using the switch, and the LED light went off. In the middle shows the load frame, which we used a trapezoidal cycle we controlled. This is a cyclic load. It represents the most like a footstep, where it consists of a negative 10 pound amplitude, so 0 to 10 pounds on the transducer, and ramps being 100 pounds per second, so it applied 100 pounds per second until it hit that negative 10 pounds, or it hit negative 100 pounds per second until it hit negative 10 pounds, with a hold of 0.125 seconds on each trapezoidal flat, so at 10 pounds and at 0 pounds. And on the right is the completed circuit. As seen, it's not complicated. It can be easily repeated.
Here are the results from our test. So we used, in this case, just one single transducer under 4 different loads of 5, 7.5, 10, and 15 pounds in the load frame. So these are plots of voltage over time. And as we can see for all of them, they sort of reach a peak voltage and then start to plateau. And we can kind of see the same thing in the parallel and series setups. So here we took 2 transducers and wired them in parallel and series, and then used a 10-pound loading in this case. But as we can see for the parallel configuration, we reached a higher voltage in a shorter amount of time, but kind of with some more variance. And then the opposite happened in series, so we reached a low voltage, but had kind of less variance. And we can see that in the parallel case, if we kept going up with more voltage, then we would come out with more variance. So here is from our uncertainty analysis. So the only real kind of problem we have here is from the first voltage under the 5-pound test, but that's due to some of our own error. And every other number looks really good. We can see that the confidence intervals are really well within like 90 to 95% of the average. And we did the same thing to the parallel and series configurations and came out with the same kind of idea of the 90 to 95% range of the confidence interval to the average. And both turned out to be really good and viable tests. And just to kind of reiterate some things, for higher loads, we saw higher voltages, which aligns with our hypothesized outcome of what we assumed would happen. And we saw the highest voltage of 5.003 during the 10 and 15 pound test. And the parallel configuration provides a higher voltage output, but higher variance, like I was saying. And the series configuration shows less variance, but a lower voltage output. And from our uncertainty analysis, we can see the graph in the bottom, where you have pretty small margins of error. You can see these graphed in the average. And we had the confidence interval within a really good range of 90 to 95%.
So now we'll start to look at the neural network modeled for this experiment. It has 2 inputs, which are the voltage for each trial, and then it goes into 10 hidden layers, each of which have a weight and a bias. With these then sum into a sigmoid function, and then these get sent into a single output layer with a weight and a bias as well, which then sums into a linear regression. And eventually we'll get our output, which is the time for specific voltages to occur. Like I said, the inputs are the iterations of testing, just for a broader sample. The output is time in seconds for each iteration, and we used the 7.5 pound force test for this neural network, and we would have to expand on it with some of the other test data if we wanted it to be accurate across more cases. So this is the prediction of the neural network given just the testing, and no extrapolation or any type of prediction beyond what we gave it. So basically what this tells us is that the actual time matches up with the predicted time of the neural network within this region of testing. So basically if we were to give it any voltage from, say, 0 to 4.5, the neural network would very accurately predict what is going on within the actual results. But from this, if we were to, say, give it a voltage of 6, we'll see coming up here that it's a lot harder for it to get it right with just given the test. So here, the data has been extrapolated to 500 seconds, rather than the original, I think, 250. And as you can see, the voltage flattens out quite a bit, which can be expected when, with these piezoelectric discs, they can't exceed a specific voltage even if you keep forcing them. So the prediction here is a lot worse. The predicted voltage and the time do not match up as well because the model isn't accurately predicting this leveling out, which creates some inconsistencies. So this kind of helps to give us a direction in the future that we would go, which would be to feed this system some more data from the actual test, and then hopefully the network would give out better results for higher voltages and understand the leveling off. This is the helper function that we used in MATLAB to basically give ourselves inputs for the neural network and manually put them in to see what our results would be. I did a quick example here, throwing in 3.2 and 3.4 volts for each iteration. As you can see, it gave us a result of 142.55 seconds, which should be extremely accurate based on the fact that that is within our range of testing. And then this just outlines the performance of the neural network. You can see up to the left here, the mean squared error is quite high right when the neural network starts. And then as it passes through the hidden layers, the mean squared error drops quite a bit. And you can see that the neural network becomes quite accurate, which is what we want. So that's definitely good. But like I said before, if we expand upon the data set, we're going to see some not so great results with the mean squared error and need to make some changes to the neural network to get a better prediction.
There's a few sources of possible error in our experiment. This included the human error in reading the voltmeter data at the correct timestamp. Trapezoidal strokes seem to bind up sometimes. This could lead to inaccuracies when using the load frame, and there could have been circuit inconsistencies when performing the experiment. If we had time to do more work on this experiment, we'd test additional transducer configuration, including arrays of 3 or more in series and parallel. We compare the performance under varying frequency and amplitude of cyclic load. We'd integrate an energy storage circuit with voltage regulation for real-world applications, investigate long-term durability and charge consistency under repeated loading, explore the use in floor tile prototypes for kinetic energy harvesting demonstrations, and we'd add a load resistor to the circuit and compare it to the unloaded results.